Hi Bobcats! In this video we're going to take a look at the connection between the acidity of a molecule and its structure. The main idea that we're going to focus on is that the bond between the acidic proton and the rest of the molecule, the conjugate base, is key to how acidic the molecule is. If we have a weaker bond between hydrogen and the rest of the molecule, then it will be a more acidic molecule. A stronger bond holds to that proton tighter and makes it less acidic. There are two big factors that will affect that. The first of those is the size of the anion. So this would be, say, for the hydrohalogen acids or the ones where the other atom is a chalcogen. And the second factor is the electronegativity of either the anion itself, or in the case of like organic acids, atoms that are attached nearby. The first of these factors that we're going to look at is based on the size of the anion. So for instance, HF is less acidic than HCl, that's less acidic than HBr, and that's less acidic than HI. In fact, the difference here between HF and the rest of them is so big that HF is a weak acid, whereas the rest of those hydrohalogen acids are strong acids. By doing some fairly sophisticated experiments, we can actually even determine that the acidity keeps increasing as you move down the periodic table for that other atom. But for our purposes, let's just take a look at the big idea here. The bond between hydrogen and the halogen is formed by the overlap of the hydrogen's 1s orbital with a p orbital on the halogen. And for the smaller halogens, the overlap is fairly large, but if we get up to the bigger halogens, like iodide's a really big ion atom, then this little hydrogen atom overlapping with it, that's just a little teeny tiny bit of overlap, relatively speaking, whereas that's exact same amount of overlap with something like fluorine, which is so much smaller, is more significant. And remember, the size of the atoms increases as you move down the periodic table, right? So the fluorine atom is much smaller than chlorine, which is much smaller than bromine, and the biggest of these is going to be the iodine. So as that halogen atom gets bigger, the overlap between the orbitals gets smaller, and the easier it is for the proton to ionize. Take a moment and think about this question. Out of this series of acids, which one of these is going to be the strongest? You may want to pause the video to give yourself a moment. All right, let's analyze this. We're trying to compare oxygen, sulfur, and selenium. When you look at the periodic table, these are all chalcogens. Oxygen is highest in the table, followed by sulfur, followed by selenium, which means oxygen is the smallest atom and selenium is the biggest, talking in terms of, say, atomic radius. And so the bigger that atom is, the more acidic the compound will be. So the most acidic, the one that will be the strongest, is H2SE. The other factor we're going to consider is the electronegativity of atoms that are near the hydrogen in the molecule. So for instance, in the chlorine family of acids, we can compare hypochlorous acid, HClO, with chlorous acid, HClO2, and chloric acid, HClO3, and finally perchloric acid, HClO4. The HClO4 molecule will be the most acidic of these because it has the most oxygens on it. The least acidic is going to be HClO. What's going on here is that adding those oxygen atoms to the molecule causes electron density to be shifted over towards the oxygens and away from the hydrogen. So as that electron density is shifted away from the hydrogen, it's much easier for that proton to ionize. The more electronegative elements we have nearby, the bigger this effect will be. So having 4 oxygens withdrawing electrons in HClO4 makes it really pretty acidic, and having just a single one makes it in HClO makes it less acidic. Also note that both HClO3 and HClO4 are strong acids, whereas HClO2 and HClO are weak acids. Another place where we can see this comparison is in substituted acetic acid molecules. Acetic acid is, let me switch over to the laser pointer. Acetic acid is the molecule over here on the far left. It consists of that carboxylate group, the C double bond OH group, and remember that the acidic proton in this type of molecule is the proton that's attached to the oxygen. So in all of these related molecules, the acidic proton will be that one. The difference here is in just plain acetic acid, the nearby carbon is attached to 3 hydrogens. That's a completely non-polar bond. There's no tendency of the exterior atoms, the hydrogens, to be pulling electrons more strongly than the carbon. But if we move over one molecule and look at fluoroacetic acid, one of those hydrogens has been replaced by a fluorine. Fluorine is so electronegative that it just sucks the electrons over towards it. It just pulls on them very, very strongly, and it shifts the electron density away from the proton that's over on the other end of the molecule, making fluoroacetic acid more acidic or stronger than just plain acetic acid. And then as we move to difluoro, where 2 of the fluorines have been substituted, or trifluoro, where 3 of the fluorines have been substituted, or 3 fluorines have substituted for hydrogens, as we just keep adding those more electronegative elements, they just keep pulling on those electrons more strongly and making the acidic proton even more acidic, making it much easier for that acidic proton to leave. So let's put that knowledge to the test here with these molecules. They are all based off of acetic acid. So acetic acid is kind of the starting point for comparing all of these. In molecule A, it's called chloroacetic acid, so that indicates that one of the hydrogens has been replaced with a chlorine. Chlorine is fairly electronegative. In answer D, we have fluoroacetic acid, which would indicate that one of the hydrogens has been replaced with a fluorine. So if we were to compare the molecule in answer A with the molecule in answer D, the fluoroacetic acid in answer D will be more acidic because fluorine is more electronegative than chlorine. And so it's going to withdraw that electron density more so than chlorine will. And we just see even more of that effect with the molecule in answer B, where 2 of the hydrogens have been replaced with fluorines. That's what that difluoro out in front means. So the strongest, the most acidic of these molecules is molecule B. Now, if you're kind of nodding your head and going, yeah, the more electronegative one makes the molecule more acidic, but I don't know which atom is more electronegative. Remember that electronegativity from Gen Chem 1 is a periodic property, and different books and different professors present these in different ways. I normally present this by sketching the periodic table just as a big old rectangle. And the biggest values of electronegativity are found in the upper right-hand corner of the periodic table, with one significant exception. We exclude noble gases from this trend because electronegativity is a property measured within the context of a chemical bond. And generally speaking, the noble gases don't form bonds. So the biggest, most electronegative element is fluorine. It's arbitrarily assigned a value of 4.0, and all of the other elements in the table have electronegativities that are smaller than that. So if we're comparing fluorine and chlorine in this problem, fluorine has a bigger electronegativity than chlorine, and of course hydrogen is much lower. And so the choice that has the most fluorines will be the most electron withdrawing, which will make it the most acidic molecule.